So, welcome back. In earlier video, what did we discuss? We discussed three types of processes or interactions of photons with any matter. One was absorption, another was spontaneous emission, and this third one, whose name you cannot read unfortunately, it is called stimulated emission. We found out the rate for stimulated emission, spontaneous emission, and absorption. And now our journey starts. What do we want to do is, for a thermal equilibrium case, what do we mean by thermal equilibrium? Basically, right now, for the time being, the temperature of the body does not change. That is called thermal equilibrium. So for any thermal equilibrium, if this is atom, there are some, these are energy levels, E2, E1. There are some atoms in the ground state, some atoms in the excited states. The photons come and photons go because of emission. Photons are absorbed, then they are emitted. This process keeps on happening. For thermal equilibrium, the rate of absorption should be equal to the rate of total emission. That is why we call it equilibrium, right? The rate of absorption should be equal to the rate of emission. Now, immediately one question will come into your mind, that there are two kinds of emissions here. Which one should we take? Answer is both of them. So rate of absorption is equal to rate of spontaneous emission plus rate of stimulated emission. SP is spontaneous, ST is stimulated, and this is the rate of absorption. Totally in thermal equilibrium, these guys has to be following this relation. Now what is R absorption? It is B going from 1 to 2, depends on N1 and rho of nu. More density incoming photons, more will go up. More particles in the ground state, more will go up. What is rate of stimulated emission? It is again B, because stimulated, some photons are coming, so it depends on rho of V, B going from 2 to 1, and depends on N2, because more atoms are there in the excited state, more of them will come down. And the third one is A going from 2 to 1, only depending on N2. This is for spontaneous emission. From where did I wrote these equations? Previous videos, or these three equations. I have just written them here. Now, if I make rho of V the subject of this equation, rho of nu, then what does it become? It becomes A21 N2 divided by, it is how much? Yeah, B12 N1 minus B21 N2. This is rho of nu. What I have done is, again, I took this term, this side, it became minus, then took rho of nu common out, and then sent the multiplication of rho of nu into the denominator. This is rho of nu. So now we are going to divide this entire term by a factor called B12 and 2. We are going this entire right side in numerator and denominator, we are going to divide it by B12 and 2. Why? It will be immediately clear after 3 steps, but this step is very crucial if you want to remember the, what we can say, the derivation. Ideally it is this point which I would also tell you to remember, this point, but the reason, if you understand the reason, then it becomes very clear. So let's divide this by B12 and 2. So rho of nu, it becomes A21 over B12, N2 N2 cancels away, so it is N2 by N2. Let's just write it for the sake of completeness. B12 N1 over B12 N2 minus B21 N2 divided by B12 N2. For the sake of completeness, we have written this. Now this goes away, this goes away, and this goes away. So this will become nothing but A21 over B12 divided by this big denominator N1 by N2 minus B21 by B12. This is a big ugly looking equation. Probably you don't like to look at it this way, or probably you like to look at it this way, but we have to understand one more thing now, that the population of the levels, so this is something that we know, the population of levels are related by this Maxwell-Boltzmann equation, and that Maxwell-Boltzmann equation is n2 by n1 is equals to e raised to minus e2 minus e1 divided by kt. This is called Boltzmann equation or Maxwell-Boltzmann equation. The relation between n2 and n1, relation between population in excited state and population in ground state, is given by this equation. So this one we have discussed in the class, right? So that relation is given by this equation. Now, if you put this here at this place, you of course have to invert this relation, but everywhere e2 minus e1 here, we know how much was e2 minus e1 everywhere. Let's just focus on our processes. E2 minus E1 here, it was equal to h nu. E2 minus E1 equal to h nu. E2 minus E1 equal to h nu. Everywhere E2 minus E1 is equal to the energy of the photon, that is h nu. Therefore, we can replace this, and I'm inverting it. Remember, I'm inverting it. N2, N1 by N2 is equal to, N1 by N2 is equal to e raised to plus h nu over kt. Why did it become plus? You have to be very careful here. It became plus because I inverted n1 and n2 from n2 by n1. So this minus sign went up. Yes. So now if we put it in this equation of rho of nu, that equation looks like a21 b12. I don't remember it, so ideally you should also not remember it, but since you have to give exam, what can we do? Minus, how much is it? b21 over b12. But you should remember this derivation because it is very straightforward derivation. It just comes from the basic understanding of absorption and emission. So this derivation is not difficult part, absolutely not difficult at all. What is difficult is probably this particular step. You have to divide by this particular number, and you should keep in mind. Otherwise, it will be very easy later on. So this is rho of v or rho of nu. Now, if you take out this a21 over b12 outside, becomes something like this: 1 over exponential of h nu over kt minus b21 over b12. Just came out to be this. This is rho of nu. Rho of nu means, again, let's understand its meaning first. Its meaning is the density of incoming photons. This is nothing but the density of incoming photons. So there was a guy whose name was Max Planck. He was a scientist, and he wonderfully found out that when you heat up a body to some temperature T, it also emits some photons. And the photons that are emitted by that black body is given by this formula rho of nu equal to 8 pi h mu cube over c cube 1 over exponential of h nu by kt minus 1. This formula, again, very difficult to remember for me, and I would not remember it anywhere in my life, but you have to give exam, so you have to remember this formula, that this was the density of photons coming out from the black body radiation. Rho of nu is equal to this. Now what are every individual terms here? So nu is very easy, it is the frequency of the outcoming photon. Only nu guy is mu. Mu is the refractive index of the material, of medium. C is nothing but speed of light, 3 into 10 raised to 8 meter per second. 8 pi h is the Planck constant, mu is the frequency of outcoming photon, and this term. This was the density of photons coming out from the black body radiation. These were the photons which were incident on the material to produce absorption and emission. So density of photons should be density of photons. जहाँ से निकलते हैं photons from black body या जहाँ जाते हैं, density should be same. This was the idea that Einstein used. The density has to be same, and if density is same, you compare these two formulas. Exponential of h nu by kt is same. Exponential of h nu by kt is same. Now you remember why did you divide by b12? Because we wanted this exponential of h nu by kt here, because after that these two formulas will be similar, and these two formulas will be similar, so b21 by b12 will be 1, and this ratio is equal to this. So I am writing the ratios. First ratio is a 21 over b12, it is equal to 8 pi h mu cube over c cube, and the second ratio is b 21 over b12, it is equal to 1. This is equal to 1, and the other term is equal to the other term. Therefore a21 is equal to 8 pi h mu cube over c cube b12, and b12 is equals to b21. These two equations are called the relations between Einstein's coefficients, because A12 was Einstein's coefficient, this was Einstein's coefficient, this was Einstein's coefficient, and this was Einstein's coefficient. So this relation is called the relation between Einstein's coefficients. These two are called the relations between Einstein's coefficients.